Now the concept I want to introduce is this one, modeling the experimental data. You see, we are looking at things now from the other way around. Usually we look at the experimental data. Now we are looking behind the experimental data. What happens when the experimental data generated by nature? So, I will not go through this definition, but I suggest you read it at some stage. This is the definition of modeling which was given by Pierre-Simon Laplace. It was at the end of the 18th century. It's interesting to see how he could look at the reality. The idea is that if we, according to Laplace, if we knew the effects of all forces acting on a system in a given moment, we should be able to predict the outcome of the system by using the universal language of math. Okay, so that was his idea. Of course, with yours, that is what happens, because our systems are really very complex. Laplace was studying not really simple systems, but you know, the Earth, the Sun, the planets, the solar system is not influenced by a lot of external forces, unpredictable forces, I mean. When we come to agriculture, we find systems which are under the effects of a lot of forces, which are difficult to predict. Let's think about the weather. We can't predict the weather for next year, so we can't predict the yield for next year if it is taken in. So our systems our models become very complex, and in the end, we are not able to really predict everything in the system.
Our environmental system all the time.
Yeah, that's right. They are all changing, so we cannot really predict something which is under the influence of meteorological variables, because we are not able to predict the meteor stuff. So we are in trouble. But in any case, what I'm aiming at here is modeling the past. I have one experimental outcome, and I want to model the outcome which I have already observed. That's different. I'm not modeling the future here. We could do that. We could try to do that, but not in this course. In this course, we will be concerned with modeling the past. I mean, the experimental outcome. So it's rather humble thing, but it's challenging. You will see. So, what is my view and our view now? The view is this one. Every past observation is produced under two types of effects. This is basic. Deterministic effects. These effects are working under a cause-effect relationship. Okay? But then there are stochastic effects. And these stochastic effects, which we have called random errors, random variability, these stochastic effects are purely random. Okay, so two types of effects, deterministic and stochastic. So we need to build models which have two parts, a deterministic part and a stochastic part. Okay, these models are not mathematical models, these models are statistical models, because they contain a stochastic part, right? So what about the deterministic part of the model? It is written in general mathematical terms like this. So we have an outcome Y. Look at the subscript E, that means expected. Because we don't really observe it, we see. So the expected outcome for the system is a function f of some external predictors, which we call x, by way of some parameters theta. Theta means the full lot of parameters. For example, you know the straight line, no? It would be 0 plus b1x, then b0 and b1 would be the parameters, but we'll talk about this in a while. So we have a stimulus x and the response y. We could talk about cause-effect model or dose response model. The dose is x and the response is y. Okay, it's not always a dose. It might be a genotype, it might be a chemical product, or whatever. It's our experimental treatment which causes the response Y. And it produces an expected outcome. Expected. I'd like to underline the word expected. So these are the components which we've been talking about right now. So this is the Newton's second law. It's an example of a deterministic effect. Okay, so just to see an equation. This is a more familiar example for you. The well is polluted with a herbicide. The concentration of the herbicide is 120 grams per liter. Okay, so this is the situation. This is the truth. But normally we do not know anything about the truth. Then we collect a water sample and measure the concentration. So my question is, what is the result? Okay, so that would be a simple model, a model of the mean. That means the expected outcome, the expected concentration should be equal to mu. That is the truth, 120 grams per liter. Okay, so observations should be equal to some expected value under the effect of a certain experimental treatment. In this case, we would have water pollution, that is the treatment. Okay, in this very simple model, it is called the model of the mean. We have one parameter, that is U, and no predictors, because we have just one experimental treatment. So, that's one point, no predictors. And we do not need predictors, as we have only one stimulus. Okay? This would be something like a mensurative experiment, so it's not a real comparative experiment. It's the simplest experiment we could do. Another example, which is a little bit more complex. I want to compare two winter wheat genotypes. Let's say two winter wheat varieties with different genotypes, because we could have varieties that are indeed the same genotype. So I want to compare two different genotypes. In this case, I cannot use the model of the mean because we have a stimulus, two levels of a genotype. So I need a more complex model. And it's something like this. So the expected outcome is equal to mu A if the genotype is A, and it is equal to mu B if the genotype is B. In general, subjects treated with A return a response equal to mu A, a certain value, and subjects treated with B return a different response. Okay, so in this case we have one predictor that is described by using a categorical variable, because the predictor might be for either A or B. So it's a category. And two parameters, because we have mu A and mu B. Right? So this is a more complex model. This is called, with slightly loose language, an ANOVA model. You've probably heard about the ANOVA. The ANOVA is a statistical technique, that's an acronym, which stands for Analysis of Variance, ANOVA. And it's a statistical technique which is used to evaluate the effect of categorical predictors. These models here lend themselves to the ANOVA technique, so we call them ANOVA models. Okay, so the ANOVA is something different, but it is connected to this type of models. So I call them ANOVA models. Okay, so we have already two models. The model of the mean, simple. The ANOVA model, slightly more complex, which is used to describe the results of comparative experiments. Another example. The yield of wheat is related to nitrogen fertilization, right? When everything else is kept constant, of course. In this case, we need to use a different model, and that is a linear model, linear regression model. The yield y is equal to a linear function of the fertilization dose, that is x. So we have two parameters, a and b, one quantitative predictor, because the dose is the quantity, and the outcome is also quantitative, because we have yield. It was quantitative before as well. Okay. So you see, these are all example models, and we could make them more complex. For example, this one is the second order polynomial. You recognize it because you've seen it at high school. Or this is an exponential model. So these are slightly more complex models to describe slightly more complex experiments. Okay. So, in this case, we use these deterministic models to predict a deterministic outcome. Because these models give us, in response, a single value. Now we'll try it. Of course, the models need to be fully specified. What do I mean by fully specified? For example, with this model here, I can predict the outcome if I know A and B. Otherwise, how can I predict the yield if I don't know A and B? I need to know the specific values of A and B. In that case, I have a dose, I include it in the model, and I get the rest. Is that clear? Pretty simple. Okay, in this case, we don't need to make predictions. We have we don't need to make calculations because we have a well. It is polluted with an herbicide, and the concentration is 120 milligrams per liter. My expectation is that if I take a sample of water and I analyze it, my response is equal to 120. You agree? Okay. Again, here, the yield response of wheat to nitrogen fertilization is linear, with A equal to 20 and B equal to 0.3. I can predict the response. I take the equation, I imagine a certain dose of fertilization, I substitute to X and calculate Y. I treated is clear. But things are not so simple. Okay? Due to the experimental error, we do never observe the expected outcome. Experimental errors act at the individual level. Okay, so each experimental subject is affected by the experimental error independently from the other subjects. You remember when we were designing experiments, we had replicates, but we had control, but we also said control is not enough to avoid all errors. So we do our best to avoid errors, but we cannot avoid them completely. So we have errors, and that causes the expected outcome not to be realized. First. Second, we have replicates. So we have more than one subject that is submitted to the same treatment, and all these subjects end out to be different. But the error acts independently. That is important, because if it acts independently and if it is random, then some units will be affected positively, some other units will be affected negatively. So when we calculate the mean, we do hope that the error will compensate. That's our experimental job. And there is randomization, you remember. That ensures that the errors are independent, because we have randomized. Okay?
That means when we have a graph change the result, we will make the...
So now the problem is this one. We have this deterministic outcome and we know how to model it. My question is, how can we model the stochastic part? Because if something is stochastic, random, how can we model it? That is, because it's purely random, it occurs by chance. How can we model?
Calculating the mean or something like that. So we could get to the one point that is maybe not common, but includes everything.
But, yes, you are right. But my question is, I want to predict one subject.
Okay.
But the mean for the population might be 120 liters. That means the water is polluted with 120 grams per liter of a certain substance. Okay, you take a sample. If you take an infinite number of samples, you can be sure that the average is 120 grams per liter. That is what you were talking about. But if I take one sample, how can I predict the value? That is my question. One single sample. Because I can make predictions about the population by using the expected outcome. But that is my attitude. I think that I can predict the average behavior of the whole population. But we have a sample composed by 3-4 individuals. How can I predict the outcome of these 3-4 individuals? So, indeed, what we do, we don't use a mathematical model for this. We can't. Because there is no cause-effect relationship. Because it's chance, random. Okay. So what we do is this one, and this is very important. We write the model. That is a simple model of the mean. The expected outcome is 120 plus a value which we call epsilon. Okay. And so we see that epsilon might be positive or negative, whatever, we don't know. So it's purely random. Okay. And we use epsilon to write a stochastic model. I mean, we can't really predict the exact value of epsilon, but we can predict the probability of obtaining a certain value of epsilon. Look at this. We cannot model a stochastic effect, but we can sort out the outcomes in terms of their probability. For example, for the polluted well, we know that possible errors should be small because we exerted control when we made the experiment. We did that well. Thus, getting a concentration of 120 grams per liter, here is milligrams, sorry, is very likely. And in that case, epsilon would be 0. A concentration of 100 or 140 grams per liter should be less likely. That would mean that epsilon is equal to plus 20 or minus 20. And the concentration of 80 or 160 should be much more unlikely. So you see that the values of epsilon have different degrees of probability. 0 is the most likely value. Then 10 is 10, either plus or minus 10 is less likely. Plus, minus 20, even more less likely. Okay, so the higher the value of epsilon, the lower the probability. So you see that we can write a stochastic model to depict the probabilities. Okay, so I could write a model that does not predict the outcome, but it predicts the probability of a certain outcome.
How will we account that? How do we
Yeah, you do your experiment.
Yeah, I want to know my answer.
Yeah, it's easy. You calculate the mean, and you calculate the residuals from the mean. And that's epsilon. Because the mean is the expected value, what you observe is different from the mean, the difference is epsilon. Look at this. Look at this model here. Look at this. What is epsilon? Epsilon is equal to y minus the mean. 120 should be the mean, as we pose the problem here. We are modeling the expected outcome, that is the mean of the full population. So if you take 4 individuals, and we will see this again later, but if you take 4 individuals and calculate the mean, you can expect that the mean of the 4 individuals is close to the mean of the population, so you can calculate epsilon. But this is not what I'm interested in. I'm not interested in calculating the epsilon. Because the epsilon values are just a sample of all possible epsilon values. So I'm more interested in writing a model to depict the probabilities of the different epsilon values. And you probably heard about probability functions. What is the probability function? Probability function is a function that describes the probability. I have a possible outcome and I calculate its probability. What does probability mean? But you probably know. The probability is the ratio of the favorable cases to the whole number of possible cases. So, if I have, for example, if I have a dice, there are 6 possible outcomes, 1, 2, 3, 4, 5, 6. What is the outcome of 1, for example? It is 1 divided by 6. What is the probability of 2? It is 1 divided by 6 possible cases. If you launch the coin, what is the probability of getting heads? 1 in 2. 0.5. So that's the probability. That's the frequentist definition of probability. It is not the only definition. Watch out. It is the most natural definition, but it's not the only one. Okay. Otherwise, we would not be able to calculate the probability of, for example, getting a gain from from buying the capital of a society, because we simply cannot enumerate the possible outcomes. So there must be other definitions of probability. But never mind, we are concerned with the frequentist definition of probability here. So how is a probability distribution function like? There need to be just two main rules. The probability P must always be positive. We cannot have negative probability. And you understand it. That's natural. The probability for all possible events must sum up to 1. So, if I have 6 possible outcomes, I have 1 out of 6, 1 out of 6, and so on, and the sum is always 1. That is a rule. Otherwise, if it doesn't obey to this rule, a function cannot be a probability function. Okay? If we have ordinal events, for example, the dice, these are ordinal events because we know that 1 is less than 2 and so on, we could build cumulative distribution functions. We've seen this already because we already talked about cumulative frequencies. Well, the probability is a frequency. Nothing less than a frequency, a relative frequency. Okay? So, this is an example. Relating to the number of lateral pillars in width. Okay? So, we found, in this case, that was an experiment. We inspected 20 plants and counted the number of lateral pillars, and in 4 cases we found none. So the probability of x equal to 0 is 4 in 20. That is 0.2. Okay? Then we found 6 plants with 1 lateral pillar. Then the probability is 0.3. 8 in 20 had 2 lateral pillars, that is 0.4, and 2 in 20 had 3 lateral pillars. So the probability is 0.1. And you see that if we sum, we get 1. This is a probability function. All the probabilities are positive, so this is a probability function. Categorical probability function. But that doesn't help us at the moment, because we have the concentration of atrazine, which is a continuous variable. So we need to write a probability function for a continuous variable. Okay, this was the PDF. This is the corresponding cumulative density function. Okay, the cumulative probability function, but we use the word density for a reason that I will tell you. You see, the probability of one event and all its prior events. Okay, so
Simulation.
yeah. I will skip this. I just want to tell you that if we talk about a continuous phenomenon, such as the concentration of a toxic substance, we cannot write a probability function. Because we have, think about this, if the concentration can go from 0 to 200, we have an infinite number of events, of possible events from 0 to 200. And so we should write a probability that is a ratio from the expected event to the total number of events. So we would have infinity at the denominator, which is 0. So we simply cannot calculate the probability for a point event. But we can calculate the probability for an interval of events. So we take a scale from 0 to 200, we divide it in steps, and we can count the individuals in each step, and we can relate the number of individuals to the width of the scale. And that would be the density. That is something which we can calculate. We can also calculate the limit. Okay, but that doesn't matter. I'm not interested in the mathematical foundation of the whole thing. I'm interested to let you know that we can calculate the probability of nominal events and the density of continuous events. And for continuous events, the density is the limit of the probability when the width of the interval we select from the scale becomes smaller and smaller, tending to 0. Okay, so the concepts of density and probability are strongly connected, but they are not the same anyway. So, this would be a possible PDF. So, you see, this is a continuous phenomenon, that is the concentration. I divide the scale into steps, and I count the possible outcomes in each step, and I build a histogram like this. Then I can imagine that the steps become smaller, and smaller, and finally I get to a continuous function, which you can easily recognize as the normal density function. That is the Gaussian density function. What is it telling us? This is telling us that the most likely value for the concentration is 120, because 0 is the most likely value for epsilon. And then the likelihood, or the probability, which is the same, decreases, and decreases symmetrically to the right and to the left. Okay. Because if we can use this function here to predict not the outcome, but the probability of the outcome. So I could ask you, what is the probability that we get 120? Well, we cannot really calculate the probability of 120. We can calculate the density, but we are not interested in the density. So we work with the interval. What is the probability of getting less than 120, for example? What is the probability of getting more than 120? How can we calculate this probability? Well, we can calculate the area under the curve. Okay, so that is what we do. We take a probability density function, and we calculate the outcome of values of intervals. And we can reason, for example, if I ask you, remember, every probability function must be such that the sum of all these probability is 1. So what is the integral of that curve from minus infinity to plus infinity? So we should sum all density and get 1 by definition. So the whole area is 1. And if I ask you, what is the probability of getting a concentration value which is lower than 120? 0.5, right? Because the curve is symmetric.
Yeah.
And then the area under the curve from minus infinity to 120 must be 0.5. But we can calculate whatever area we want by using the integral, and we will do it now. Let me see, this is the equation of the Gaussian density function. Look at it and forget it. Okay, if we don't need that.
I won't remember it.
Okay, I don't remember either. So no problem. But just to let you see that there is a model which is used to calculate probabilities. Okay. Some interesting things. The shape of the Gaussian curve is only determined by mu and sigma. Is two parameters, mu and sigma. Mu is the mean, and sigma is the standard deviation. Okay? The probability is expressed as the area under the curve. The area under the curve from minus infinity to infinity is equal to 1. You've seen that?
This is one just like the unit of expression?
Yeah. The probability is the lowest, the fastest we go from the mean. The mean has got the maximum probability and then it decreases. The curve is symmetric. High values are as likely as low values. Okay, that's interesting. Why do we use the Gaussian curve? Because it's really, we can imagine that the experimental error acts like this. We don't have any hint about the fact that positive error should be more likely than negative error. So we can think that they are more or less the same.
So it's related to random.
Yeah, that's right. That's related to randomization. Okay, it is not always true. But we assume most of the times that this is true. Okay. Now, it is my idea that we, I show you this, and then we get a cockpit, and I pay for the cockpit, because it's my turn. We get a cockpit, and then we make some exercises with this function. This is our model. It's a two-component model. On one side, we have the deterministic part, but then we have this stochastic part, and for this stochastic part, we write a probability function. In this case, we have a normal probability function, and you see, we don't write it is equal. It is distributed as, because we do not know the exact value of epsilon, but we know that these values appear by following a Gaussian distribution function, so that some values are more likely, some other values are less likely. Okay, so what we know about the error is that the mean of epsilon must be 0. Okay, because in that case the concentration, the average concentration is 120. So the problem is always the same. We have a polluted well with a herbicide at a concentration of 120 milligrams per liter. Measuring errors are Gaussian distributed. So if we are making saying something more about the error here. So we are saying that the error is Gaussian distributed, normal distributed. Okay, with mean equal to 0 and standard deviation equal to 12. Okay, so this is our situation. A well that is polluted, and the error, which is probably relating to the instrument, the measuring instrument.
Or the person using it.
Or the person, but probably the person is doing his job well, according to some approved protocol. So it's mainly a matter of the instrument. But you're right, it must be the person who is collecting the sample, or who is doing the analysis, or whatever. And that causes a standard deviation of 12. Okay, so when we measure, we don't necessarily obtain 120 as the result. We might obtain more or less, okay? And the probability of getting a result which is very far away from 120 is rather low, but it is not impossible, nonetheless. Okay, so answer the following questions. First question, what is the expected concentration? We don't need to make calculations.
It should be 120.
It should be 120.
Yeah.
Okay, so this, we need to be agreed about this. We are modeling the expected behavior. And the expected behavior is the mean of the Gaussian distribution. What is the density as a probability, but we can't talk about probability, we talk about the density of something water with concentration equal to 120. We don't mind about this, but I want to show you how we can calculate this. Okay, so let's go to R. Open an instance here of our studio. Sorry, making several mistakes with this keyboard here. So here is my R console. Now this is the, I'm opening a new script, 5. And what you want to probably do now is to clean everything, because we are starting a new job, and whenever we start a new job, we clean our desktop. At least this is what we are supposed to do. I'm not doing that, but never mind. To clean the desktop, we use the command remove list equal ls. Okay, so this might be our first move when we start a new project. And then the second move is probably to save the code before we forget. So, file, save as, and we give it a name. For example, so model. And we say, but you can give it whatever name you would like to give it. Okay? So now my first question. Gaussian density. So we have a function. There is d norm, and it is easy. D norm, that D stands for density, norm stands for norm. We have several other probability functions, and they are always named like this, D followed by the name of the function. So we need to say, what is the value we want to calculate the density for, and it is 120. Then we need to say what is the mean. The mean of the population is 120, because we know that the error must be 0. At least the most likely value of the error must be 0. So 120 plus 0 is 120. And the standard deviation is 12. SB equals 12. This is the correct way of writing this statement, but please remember that I could also write it like this. Erasing the names of arguments, because R can recognize them by position. In this case, because the position is x mean and standard deviation. So I gave it the value, the mean, and the standard deviation. So this would be totally the same. This is more tidy. Okay, so we don't run the risk of making a mistake with the position of arguments because we identify them by name.
Yeah.
But sometimes we are lazy and we don't want to write the names of arguments. But we should not be lazy. But sometimes we are because we have a lot of things to do.
It's not laziness, it's going fast.
Yeah, well, yes, you are right. It's going fast. Sometimes we need to go fast.
Yeah.
And it is not always a good idea
To go fast.
Okay. So now we get density. In itself, it doesn't mean anything because it's not a probability. It is a density. We cannot calculate the probability for a point event on a continuous variable. But I just wanted to show you how a density function looks like. I would like you to do this now.
Before we continue, watch out for the standard deviation. It should be 12.
Oh, sorry, you're right. Not 2, it's 12. This keyboard is terrible to me because I cannot press. So it's a little bit small. The density is smaller. Why is it smaller? I'll show you now. Let's try to plot a curve by using the d-norm function. So we use x now. That means plot a curve for the normal density for an unknown x value. So something like this. 120, 12. Now we specify that the x value should go from, let's say, for example, let's say 40 to 200. And we get the Gaussian distribution.
Yeah.
Okay. And it's interesting to note that if I decrease the standard deviation and put it, well, it's not a good idea. I show you now. And I write here edge equal true, and maybe also I'm going to a new line, otherwise you don't see it. Print it in red. You see what happens. Okay, there is not space enough to plot it. Okay, because it goes very up. But we can correct easily by specifying here each limb. So give limits for new limits for the y-axis. And we go from 0 to 0.06, 0.1. Enough again, but just to show you, you know what I mean. If the standard deviation decreases, the possible measures tend to concentrate around the mean.
Yes.
Okay. As the area under the curve must be always equal to 1, and of course the population becomes higher. The curve becomes much higher. Steep, yes, very steep. Because if the error is small, then the measures tend to be alike from one another. If the error is big, let's try to plot another one where the error is big. For example, instead of 12, we could say 50. And we could plot it in blue. And you see it's very flat.
Yes.
Okay. it increases the probability of obtaining the density, but it's connected. It increases the probability of obtaining the measures that are very far away from the mean. So, this is very important to note, in my opinion. Because we are modeling the experimental error, which changes the probability of getting measures that are not as they are expected to be. So my expectation is 120, but the error changes the observation with respect to the expectation. If the error is big, the changes are big. If the error is low, the changes are low, and I am very close to my expectation. Okay. Of course, if we change the mean, the curve moves to the left or to the right. For example, if I always tracking 12, but the mean is 100, and I print it in green, curve moves to the left. Of course, I'm moving the population. I'm changing, you see what I mean? I'm changing the location. That, you remember we were talking about location measure. The mean is a location measure. If the mean changes, the population remains the same shape, but it moves along the axis. It moves its location. If I change the standard deviation, the spread changes because the population is more spread or less spread. So you see that there is a close connection with what we were doing a couple of weeks or last week. So this is the density. But we are not really interested in the density because it's an abstract concept. It's not a probability. We are more interested in the probability. So let's go ahead. Any questions about this? The code.
Yes, Prof. I'm sending in the message. I got error. I don't know why. Before it was working, now it got error. I'm sending the code, and with the error, it's like.
Yeah. Please send the code. The C is in capital letter, and it should be small letter. So not C, for example, 40 and 200, but you correct into small c. So that's...
Prof, I wrote it in a small c.
No, it's capital letter. At least in the code you sent me, it's capital letter. Both here and here. So both are wrong. This is capital letter.
Okay, thank you. I don't know why it's written in. I'm always writing in a small c, but it's always going like a capital letter.
Well, that's, you know, computers always do what they want. We are not totally under control.
That's fiction.
They have the power.
They're controlling the world.
They are controlling us, not the other way around.
Okay, so thank you.
Thank you. So, you see that mistakes we make are always small typos. And that's the most frequent things that might happen. So if you find some mistake, look carefully at the code, because some typo might be hidden in your code or hiding in your code. So we go back to the exercise. Then the third question, this is more interesting now. What is the probability of sampling water with a concentration lower than 100?
So we're going to calculate the interval, the area.
That's right.
Interval from 100 and before.
That's right.
Till infinity.
That's right.
Okay.
That's right. And that's interesting because we might wonder, is there any possibility that we get an extreme result? So the truth is 120. But can we get less than 100? Which would be wrong. But it is possible to get it. What is the possibility? What is the probability? Right?
Yeah.
Let's calculate it. In this case, we use, calculating probabilities, not densities. Probability is more important, but we can only calculate probabilities for intervals, and the function is P norm. So, probability normal. And the syntax is always the same, but our x value is 100. And mean is 120, and the standard deviation is 12. By default, the probability is calculated from minus infinity to the value we specify there. So in this case, from minus infinity to 100.
Okay.
And that is what we are looking for. Okay. So we get almost 5% probability. So that means 5 samples out of 100 would have a concentration lower than 100. Oh, which is really wrong. But it's normal. It's normal for an instrument to have 12% coefficient of variability.
Yeah.
10%. That is, the mean is 120. The standard deviation is 12. That means that the coefficient of variation is 10%. And it is normal for an instrument to have 10% coefficient of variability. So you see that we are never, ever sure that we are doing things right. Because it's always possible, 5% possibility of getting something which is very wrong with respect to the truth. And we are obtaining that only by chance. Due to the experimental error. Of course, if the error is smaller, then the probability is much smaller. You know, so it's important that we do things well, so that the standard deviation is low. Because in that case, the risk of getting wrong is much smaller. Okay. And you can go ahead with this. Fourth question. What is the probability of sampling water with concentration higher than 140? Okay, so higher than. We have two possible lines of attack. We could run or
141,
then 120, then 12. It is so far, but this is not correct. Okay, so we can do two things. One minus this one. To do something like this. Add an extra argument, that is lower tail equals false. So we don't want the lower tail, we want the upper tail. That is the integral, the area from 140 to infinity. And that gives the same result, of course, you see. And you may note that it is the same result as before, almost 5%. And that's normal, because the distance from 120 to 100 is equal then the distance from 120 to 140. In one case the error is negative, and in the other case the error is positive. But the distribution is symmetrical around the mean. we can solve more. This is simple. What is the probability of sampling water with concentration between 100 and 120?
Okay, so the 0.5 minus the P naught.
Yeah.
That's it.
So you do something like this. You take this one. You take this one. Look at me. So I'm subtracting because I'm taking the probability from. Let me do something like this. I want to show you the picture. Oh gosh, did something wrong. Yeah. So this is my distribution. I'm taking the integral, the area under the curve, up to 120, and subtracting the area under the curve up to 100. So what is left is the area from between 100 and 120, which is what I'm looking for. So go back. Here we go. This is the area for an interval, which is a lot. There is a lot of probability of getting a value in this interval. Of course, we are close to the mean. Now we change a little bit our attitude. So far, we've been calculating probabilities. Now I want to calculate values that correspond to certain probabilities. For example, what is the 80th percentile? Meaning, what is the concentration which is higher than 80% of all possible values? So, what I want to do is to find a value somewhere here so that the area under the curve from minus infinity to this value is 80%. Okay? So, in order to do this, I have to simply switch and use Q naught. I want 0.8 that corresponds to the 80th percentile. And the population is always the same. It's a Gaussian with the same mean, 120, and standard deviation equal to 12. And so we get 130. Okay, so there is 80% probability that we sample below 130. Okay, so you see that now I do not know exactly what my result will be with my experiment. I do not know, but I can calculate probabilities. This is the best I can do, considering that the driving forces are random. So this is how a statistician thinks. So we are dealing with phenomena that are under a random force. Okay. Without meaning. Yeah. Because in this case there is no deterministic force. It's simply a well which is polluted, and we need to be able to forecast what our analysis will give as the result. And we cannot forecast, we cannot predict, but we can calculate probabilities. If the reality, the truth, is in a certain way, then the outcome might be like this. Okay, we don't know what the real outcome is, but we are we know that certain outcomes are more likely than others. Okay? So, this is interesting, number 7. What are the two values symmetrical around the mean, which contain 95% of all possible values? So what am I looking for?
Okay.
Am I looking for two values? One it is here, one it is here.
95% between.
95% is between. Of course, I could move the two values, but I said they must be symmetrical around the mean, so the same distance. Otherwise, I could move them. The problem is not specified. But if I say they must be symmetrical around the mean, then the problem is specified.
Right? You go for like 5% divided by 2 is 2.5%.
Yeah. You need to be careful because we have to have 95% in between, so that means that we have to have 2.5% above and 2.5% below. So
90. That means 5.5.
yeah, no, 2.5, 2.5, because then the sum is 5 and 95 is in between. So I could do something like this. Look for 0.025, and this would be one value, and the other one is symmetrical with respect to the mean, so I don't need to calculate it, but I can calculate it as this. Okay? So, what does this mean? This is extremely important for what we will say in about next week. We have two values, 96.5 roughly and 143.5. 90% of our measures will fall within this interval. This is very interesting, very important.
Can we put them both together so we get them as an interval? Like
No.
not to evaluate?
No. Not with this. What we could do is something like this. We do this now. We write 120, instead of making reference to the population of concentrations, we write 110, 20 plus norm 0.25, sorry, 0.5, 0, well, so we are using the error population. In this case, we get a value that is minus 23. So if we take this value and add it and subtract it from the mean, we get the interval.
Raf, pardon me, I didn't understand why you said 120 plus Q norm.
Because I could write something like this.
Okay. Can you run it, please? Okay, thank you.
And get the same value, and then I could write this one like this. Get the other value. You might say that this is unnatural because we are adding a negative amount and subtracting a positive amount. So we could do the same if we do like this, which is really very common that we do. So we write plus, and here we put 975 and 975. We get the same result exactly, but in this case, this amount here is positive, because it's above the mean, and this amount here is negative. It's still positive, but we subtract it from the mean. Okay. So we have plenty of possibilities here, but what is important is that you follow my reasoning. The reasoning is this: the result of an experiment, on average, can be predicted by using a certain model. But the observation, the real observation, cannot be predicted, but we can calculate probabilities. Okay, that is my reasoning. We predict the average behavior, and then we calculate the probability of obtaining a certain real outcome. I think we have time to do another exercise. It's more interesting to me. But first I need to drink some water. Otherwise my other questions? No questions. So,
can you just show that for
I'll give you a few seconds to write the comments. I could also check the code we've been developing here and put it in the chat box so that you can go over it and check whether you have mistakes. This is very big. But it might look a little bit odd for you because you are not used to this kind of reasoning. So you might think that if there is a phenomenon, then we should be able to predict it as long as we know the underlying mechanisms. For example, the coronavirus infection. There is an infection, and we should be able to predict it. If we are not, it is because we don't know it. In reality, we are never able to predict anything.
Okay.
Yes, because we can predict the average behavior, but then the real behavior is different because of the experimental error. And the experimental error could also be what we do not know about the phenomenon. Because that makes the fact that the model doesn't exactly reflect the reality. So we have a model which is not really like the reality. And that might cause variations from the expected behavior. So we could have the error, but we could also have a deterministic model which doesn't work well enough. Okay. Look at this exercise. This is more interesting. A xenobiotic substance degrades in soil following a first-order kinetic which is described by the following equation. So what we see here is that we have a concentration Y that depends on the time. The concentration drops with time. So, after spraying this substance in soil, what is the probability that 50 days later we observe a concentration value below the toxicity threshold for mammalians, that is 2 nanograms per gram? So this is a realistic question. We spray and we want to know, is it possible that 50 days later, we are below the threshold level of toxicity? Yeah. Well, in this case, we simply use a model to predict. Okay. But we will see that normally we do experiments to define the model. Okay, so in this case, we know the model already. Okay. This is interesting. So look at this. Now, if there were no errors, so what would be the average here? Well, we take the model. If the model is, I think here, y, so the concentration is equal to 100 by x, let me look, forgot it, minus 0.07, that's like James Bond, 007. T is time. So, if I take this equation here, I can predict, I replace time with 50, I can predict the expected concentration. Expected concentration. Sorry, I need to, I forgot the minus sign here. There we go. So it's 3. It's 3. So if there were no errors, you see that the concentration has not dropped below the toxicity threshold. Okay. Is there a perspective? In this case, you see that the reality tells us that the soil is not safe because we are above the concentration. But if we measure the concentration, can we obtain a result which tells us, okay, we are safe, we could send our cows to pasture? Okay, so is this possible? It is not, but is it possible that we obtain a result that says to us it is safe? Let's see. We know that probably the results of this experiment, the results normally distributed. I do not get 3.0.19. What I get is 3.019 plus epsilon, where epsilon calcium. My here with this keyboard is really terrible. Distributed and according to the question here. So the result should be something like this. Third, the norm 3.019, I'm approximating 3.19, and the standard deviation is, so we have a coefficient of variability equal to 20%. That means you know that the coefficient of variability is the ratio between the standard deviation and the mean. So if I take the coefficient variability and multiply it by the mean, then I get the standard deviation. So the standard deviation would be 0.2, that is 20%, by 3.019. Getting this curve from 0 here we go. This is the density for our result. So we are modeling the average behavior. That is 3.019. But you see that there is the risk that we get 2 or less. There is the risk. And it is a risk because that would mean that we say, okay, we are safe because the herbicide or the toxic compound is no longer toxic, but indeed it is still toxic. And we want to quantify the risk. Did you understand what we are doing? So we want to quantify the risk that we erroneously conclude that the compound is no longer toxic when indeed it is toxic. And we see that after 50 days it is toxic. But we might, due to the experimental error, we might observe that it is not toxic. That would amount to observing a value which is lower than 2. And we can calculate this probability by using P norm 2 population where the mean is 1. Okay. So you see what I'm doing. I'm calculating the probability that we get 2 or less when the average is 3.02 and the standard deviation is 3.02 by 02 because that's the coefficient of variation. So we still, you see that we have 4%, almost 5% probability of giving the conclusion that is wrong. So, what do you say to the person who committed you with this work? Will you say that the compound is safe or it is still toxic? If you say that it is still toxic, then you're right. If you observe 2, but it might be a mistake, you have 5% probability that it is toxic, yes. Yeah. So, we need to learn to take decisions in presence of such an uncertainty, which we can quantify. That is our advantage.
Decisions depending on calculation or ethical decisions?
Yeah.
Ethical?
Well, that depends on what we could reasonably expect.
Okay.
That is what we do usually. If there is a small risk that we are making a mistake, then we say, okay, it is safe. Yeah. But if like in this case, there is a high risk that we are making a mistake, then we use a conservative approach. And we say, no, it's not safe. Yeah. Because there is a high risk that it is not safe. In this case, 5% is rather a high risk. Okay. I mean, if you send the cows in that field, you have damage in 5 cases out of 100, which is a lot really. So that depends on your risk. Are we talking about health? Are we talking about money? Are we talking about something else? We need to calculate the risk depending on what we are studying. But still, the approach is like this. So we get 2. We might get 2. Is it safe? No. We are not sure. Because there is 5% probability that it is higher. So, this is the approach we will keep in the next days. The idea is that an experiment comes out with results that do not reflect the reality. Okay, that is the idea. The experiment is only a distorted image of the reality. And the distortion is due to the experimental error. Of course, we need to do things well so that the experimental error is small, which helps, but it doesn't solve the problem. Because the experimental error is always there. Maybe small, but it's always there. I think you could go ahead and try to do the exercise 2. Not today. The exercise 3, not today. You do it by yourself. And then we discuss it on Monday. I would like to, there's 5 minutes left. So I would like you to show how we can reproduce an experiment on the computer. For example, simulating experiment. I'm always working with the same experiment. The concentration that is 120 milligrams per liter. So if we the concentration mu is 120 grams or milligrams per liter. What we obtain if we make 4 measurements? A reasonable situation is like this. We take 120 and the expected value, as we know that the concentration is really 120, and add some errors which are sampled from a Gaussian distribution. So we take random values from the Gaussian distribution of errors. And we do this like this. Random values from a normal distribution. This is the error. So the mean is 0. So I want 4 values. And the mean is 0. And the standard deviation is 12. That was our error. So I do the experiment. And I get these values here. And of course you obtain different values with respect to me, most likely. Because your errors are different. It is simply sample. I do the experiment again. These are my results, and they are different. I do the experiment again. 4 different results. And that is what we think it is happening in nature.
So each and every time the outcome is different from the experiment.
Yes, right. And this is what we think it is happening. That is the mechanism it is working underneath.
Due to random.
Due to random errors.
Yes.
We never know what we are going to obtain. That's why science is not data. Data might be wrong.
Yes.
Science is about methods. Because if the method is okay, then the probability that the data are wrong is very low.
Science is all errors.
You know, we are back to the first lesson now.
Yeah.
Science is not about data. It is about data, but it is about methods.
Yes.
Because, of course, if we manage to reduce the error to 1 here, then you see that the results we get are very close to the truth. Otherwise, they are different. This is called Monte Carlo simulation. Monte Carlo simulation. This is a very simple example of Monte Carlo simulation. Because I'm predicting the results and adding random errors. They are sampled from a Gaussian distribution. Okay. This is terribly important. Okay, because what we will say from next week ahead will always be based on this consideration. So we think that every experiment works under that mechanism. The part is purely deterministic, and another part is purely stochastic. Okay. Now, so I think we are done. Try to do those exercises I propose. There are several proposals here. Monte Carlo method, exercise 1, exercise 2. Now, the exercises, I will put this presentation, the book chapter and everything in Unistudium maybe this afternoon or maybe before tomorrow. At least what I promise. And then we will take these exercises and work on them next Monday, because I would like you to learn this part and to practice, because this is very important. This is the fundamental of our job. Once you know the fundamental, then you can see all the rest by yourself. Okay, see you next Monday.
Tuesday, yes? Monday is the 1st of November.
Monday is the 1st of November, so it's, yeah. So see you on Tuesday.